I see simulation getting used to continue to move the boundaries forward. You know, we're always trying to improve sound quality to make the best possible product or to make the best possible product at a price. And simulation is allowing us to do that and allowing us to do that quickly and cost effectively. You know, Samsung is the #1 TV company, the #1 phone company, and they really want to make a goal to become the #1 audio company. And we were able to set up a lab here in Los Angeles with the finest people from throughout the world to research audio and solve problems like no one else can.
In 2014, the Samsung Audio Lab team was really small, and pretty much from the beginning, they were looking for a simulation engineer that could help develop new products, new technologies, while they were building up the lab.
We have built an interesting group here. We've got mechanical engineers, we've got electrical engineers, DSP engineers, programmers. When we brought Andre on board, he's a simulation engineer. And the simulation engineer is kind of like that glue that brings everybody together. So an idea can come from anywhere, we build a model in the computer, and then we can investigate it together. And it's in a form that everybody can see and everybody can understand.
We're looking to build loudspeakers that produce a clear sound with enough bass to feel enveloped. And we also want the sound to spread evenly in the room. So it doesn't really matter if you're sitting in the sweet spot on the couch or if you have to sit on the side, you still get good sound. But when the TVs get thinner and thinner and better picture quality, it's a challenge to keep up with the audio quality. We use simulations to attack these problems head on. We do simulations of transducers, enclosures, and waveguides or ports using COMSOL multiphysics and improve the sound quality from the beginning of the design process.
So there's a couple of ways that it's impacted our design workflow. First of all, for routine products, it's allowed us to optimize products significantly faster. So we don't have to iterate through a lot of prototypes. But where it's been an enormous improvement is when we start going out to the edge of technology, when we start to try to do new things. The ability to model ideas that maybe are crazy and then optimize them, you can do that in a computer and you would never even try to make a prototype.
Typically, a systems engineer will come to me with a certain set of dimensions that we can use for a loudspeaker and ask the questions, where do we put the transducer? Where's the best place to put a port? How compact can we make things? Then I can run some quick simulations that make some broad assumptions that run really fast and give him an answer in a couple of minutes typically. And then later on, when things get more detailed and we know the final design of the product, to ensure that the simulation predictions and the actual device match well, that we provide accurate estimates with our simulations. We measure in anechoic chambers or under laser scanners and then correlate those results with our simulations.
At this facility, we have two kinds of anechoic chambers. One has wedges on all surfaces, and that's called a free field chamber. And this allows us to measure loudspeakers that are used in almost any location, generally away from the walls. So you might think of a bookshelf loudspeaker or a soundbar or a Bluetooth speaker, those kind of products. The other anechoic chamber over there has a solid wall. And it turns out when a speaker is close to the wall becomes actually a part of the speaker. So for example, if a soundbar is close to the wall, it impacts the sound quality. So it makes sense to measure the soundbar close to the wall in that chamber.
The anechoic chambers provide a idealized way to measure loudspeakers. Since they take away all the reflections, we can really decouple the loudspeaker from a room.
What we do is we measure the speaker on axis, and we rotate it 10 degrees, and we'll measure it again, and rotate it, and measure it again, and we measure the whole sphere around the speaker, so we can see the way the sound is getting spread into the room.
In terms of simulations, it really helps us compare the simulations with the measurements, because in the simulations we often also assume idealized conditions where there's no reflections. In the listening rooms, we perform blind listening tests where we compare our products, prototypes, with competitors.
And it turns out most people listen with their eyes. They don't actually listen with their ears. So the TV or the soundbar is placed behind a screen that the sound is allowed to go through, but you can't see through. And we place our product and competitive products on this wall, and then a section of the wall rotates, and we can listen to our product and a competitive product without seeing it in the exact same location. Therefore, we can make an unbiased opinion about the sound quality. Of course, we'll take several listeners and we turn that opinion of 1, 2, 3, a dozen people into fact. Because once you have enough people all agreeing this product sounds good, then it really does. It's not an opinion anymore.
Because we run a lot of iterations of simulation and measurement and correlate the results to make sure that the simulations are accurate, it really helps to have the designers or the engineers and the simulation under the same roof.
So Andre's been able to build a bunch of specialized tools that answer our specific needs. And so rather than having him running models over and over and over again, he's created applications that allow our engineers to just go in and solve routine problems on a day-to-day basis without needing to enlist his skills.
With simulation applications, I can give our transducer engineers a tool where they can do their day-to-day type of calculations and simulations pretty fast. There's only a certain amount of buttons that they need to click to get to the result. It's all preset for the typical problem that they need to solve. So by letting them run the simulations, I can focus on developing new models that are more intricate and involve more knowledge of COMSOL multiphysics, and they can still run their own simulations. They don't need to come ask me every time to run a small simulation on the side.
At the Samsung Audio Lab in Los Angeles, we measure success a whole bunch of ways. First of all, on quality products that we're going to deliver to the customer that are our bread and butter. We've done this before. Can we make it better for less money? But also there's this idea of innovating and inventing new things and then seeing it commercialized in a worldwide scale. I mean, that's super exciting. And then finally, it's helping to build credibility for sound from Samsung that maybe wasn't there 10 years ago. Now today, we have the same kind of credibility we have for sound as we have for great picture quality and as we have for great phones. So in that regard, we've been able to innovate in ways that we just wouldn't have done without the simulation tools.